event. Yes, the moment you have all been waiting for.
I hope everyone is ready for our feature presentation now. Tom Murphy from the Cult of the Bound Variable.
Thanks. Is this volume okay? Okay. Well, I hope you liked our show there. This is a contest presentation about the 9th annual ICFP programming contest. Okay? So I'm going to start with the story. I don't think I need the zapper for this. A long time ago, in the year 19106, a secretive group of monks devoted to the study of computation were active in the Pittsburgh region. Stories were told of sophisticated, sand-powered computational machines, but for years, the only known evidence of this civilization was a lengthy codex, which was written in no known language. That's the no known language. Attempts to decipher it failed until, in July 2006, excavation began for a new computer science building at Carnegie Mellon. That's real. This is really the excavation. Those are two of our scientists. We have to wait for it to scroll by now. Constant speed scrolling. Archaeologists uncovered a Rosetta Stone that was the key to unlocking the codex. Here's the Rosetta Stone. Actual undoctored photograph. With it, hundreds of teams of computational archaeolinguistics researchers were able to unlock the secrets of, we'll wait for that to scroll off the screen, the Cult of the Bound Variable, the 9th ICFP programming contest, hosted by Carnegie Mellon. The judges are here, myself, Tom Murphy, Daniel Spoonhauer, Chris Casandino, Dan Licata, and our advisors, Carl Curry and Bob Harper. Now we've got a lot. We've got a lot of stuff to talk about, so I'm going to go pretty fast, even though it's an hour and 15-minute presentation. Let's start, though, with some team statistics, just so you can get an idea of the scope of this contest. We had a record amount of participation. So 500 teams were registered when the contest started. 400 more, at least, registered during the contest. 60 registered in the final 24 hours. They had no hope of winning. And since the contest has ended, really no hope of winning. 230 teams have registered. You have to be forced to register before you can do anything. So these are people that just want to try it out. And these are teams. We had teams from every inhabited continent. I'm not going to count Antarctica. We have, well, they're all over the place. These are just the teams that scored. We even had one from 0-0 of GPS coordinates. That may be a bug. Well, here are the teams that registered, really all over the place. We have a whole bunch of languages used. I've displayed this in a popular tag cloud-like format. You can see all of the usual suspects, functional languages, and some other languages in there. Also some strange things that are very small. You can look at this with your binoculars if you like. Here are the languages of choice. Since programmers these days use more than one programming language, we allow them to choose the language that was their choice in case they win the contest. Okay? All right, so a little bit about what we did. This is a graph of the lines of code in the contest, starting in March, which is when we really kind of started, up to the contest and then beyond. You can see we follow more or less exponential up until we went to sleep. And here are the number of check-ins per day. You can guess when this peak was. But that's up over 100 check-ins that day before the contest began. Okay, so I want to talk a little bit about the past contest, the history of the ICFP contest, just this slide, to give you some context for what we did. Okay, so it started in 1998, and the game was, the contest was about this game, Koos, I guess it's pronounced, which is a two-player kind of game, and programmers submitted their programs, which were pitted against one another's programs in a tournament. The year after that was a contest about optimizing these finite state machines. You had to make the smallest version that preserved the meaning of a finite state machine. After that, contest participants were asked to build a ray tracer that had to be, well, correct, was very important, and fast. Then there was a year about optimizing again, this time in HTML-like language. Then there was another tournament. This one was about package delivery, robots on a grid, and people would write robots, and they would be paired off against one another in deadly package delivery combat. And then there was one about optimizing the path of a race car by issuing commands to drive it very dangerously around a grid. The year after that was about ants on a grid trying to find food. And last year's was about cops and robbers, another tournament-style game. So for us, we really wanted to do something very different. And we particularly didn't want to do a game. There have been lots of games recently with tournaments. Nothing wrong with that. They're very fun. We've enjoyed participating many years in the past. But we wanted to do something different. We also wanted to do something really fun. We wanted to do something fun and till Daddy takes the keyboard away. See how hackers may appreciate that one. Another thing that was an important design goal is we wanted to avoid support nightmares. We've, in fact, seen talks from previous organizers that talked about how they, almost didn't get tenure or whatever because they did the programming contest. And we don't mind coding a lot, but we don't like supporting people's weird programming languages and platforms. Okay, and this crowd loves weird programming languages and platforms, as do we. So in the end, we support no languages and we support no platforms. Okay, how did we do that? Well, what we did, we talk about this Rosetta Stone. So in reality, the Rosetta Stone is a specification for a virtual machine. The virtual machine is, we specify everything about it. So your first task is to implement this virtual machine. And we give you the codex as a program that contains all of the problems. It contains the validation of the problems, and it can compute the scores. And so basically, we have to make sure that our codex runs in the machine we specify. Then you have to get it right. You have to implement it correctly, however you like. Run our program, and then you can send us the solutions. Okay? I'm sorry, you can send us the validated solutions. So validated solution looks like this. This is a string we call a publication. In the story, a researcher wants to find these publications that the scholars of the cult of the bound variable have embedded within the codex. And so this encodes a bunch of information. It tells you which problem you've solved, how many points you got, what your team number is, and then this opaque string, which actually includes some kind of team password and a hash to make sure this isn't forged. Okay? And so the codex produces these, and then we validate them. All we have to do is basically make sure they're okay and extract the thing, extract these pieces of information. And we have a live scoreboard as the contest runs. Okay? All right. So a little bit more about what we did before the contest, and then I'm going to talk about the contest itself. So one of the things we did for promotion, and this might help to explain why we had so many registrants before the contest began. Also, the success of past contests is obviously played a role in that. We seeded search engines, I should say, with this search term, computational archaeolinguistics. Before the contest started, this search term didn't really show up anywhere. Since then, we've actually taken over archaeolinguistics, which is a real field. You'll find our blogs of fictional grad students that corroborate the backstory. Some people thought they were real, though. So another thing we did is we know from our participation that we get very excited as the contest comes up. So we released this codex, which is a 2 megabyte file, 48 hours or so before the contest began. We didn't really say anything about it. It just was on there with a little question mark icon. And we said, download this, you're going to need it for the contest. And people, of course, downloaded it like seconds after the announcement went out. And they started searching in it, trying to figure out what it is. Now, we really just embedded some red herrings in there in order to let them have some fun. There's conspiracy theory stuff, Area 51. Of course, Paul is dead, naturally backwards. We embedded this logo, which is the Cult of the Bound Radio logo, de facto, in there in a couple of different formats for them to find. And they did find these, so people were really excited and mystified. Some asked us, how do I open UMZ files? We told them, wait, and you'll see. So this timeline here, which is actually scaled out to fill all of that wall, you can't see all of it, is what I'm going to be using for the talk. We're going to do this more or less in real time. Well, not in real time. We're going to shrink the time, but we're going to do it in the same order that it happened in the contest. Okay? So the contest started at the left edge of that at noon on July 21st. And the first thing that they did is this universal machine. So sand-powered universal machine. So okay, so what is the universal machine? It has 8 registers, 14 instructions, and it's really simple. There are some math instructions. You can allocate arrays and then manipulate them. You can do a conditional move or load a literal. You can read and write a single character to the terminal. And you can load a program, which means take an array and make that the new program, or you can halt. That's it. Okay? So this is, I think, a very, very simple virtual machine. And then the spec is written in this stilted language, which is meant to be humorous. I hope it was actually humorous. So it says things like, the 0 array shall be the most sublime choice for loading and shall be handled with the utmost velocity. The thing can be implemented in quite a short amount of code. So this is our C implementation. And I mean, I didn't even try to cheat by putting brackets on the same line as stuff. And it fits in 2 columns on a slide, and it really isn't very difficult to write. And it's actually not that difficult to write in other languages. Here's some of the languages that we implemented it in. Here's their score. Note this is a logarithmic scale, mainly intended to embarrass Python's performance. So we did Scheme, we did C, many C implementations, C#, Java, OCaml, Python. XML actually is quite competitive with the C implementation, especially if you turn off runtime bounds checks. UMA, I'll talk about that later in the assembly version. We did some other languages too. Here we have one of our research scientists running it on this Nokia cell phone. It actually takes a bit of time to boot it, so here I'm going to keep talking while that goes. We did one in Haskell, one in Perl, which is very painful, awk, which is extremely awkward. And of course, like everything we do at CMU, we did 2 implementations in 12 logic systems. So here it is, this is running a benchmark. It's actually extremely boring to watch, but it's running on a phone. We also wrote it in PostScript. So here we're sending the UM and a program together as a PostScript document to the printer. Hold on, he's almost there. It's where the printer room is, right in there. And this is actually a quite fast printer. There it is. It's actually outputs to the printer. You can't get input, but there's a benchmark. Everything works. Okay, great. So many languages and implementations, and this was much like how people at least attempted to do it in the contest. So we saw hundreds of different kinds of implementations, and in fact, this VM has been implemented now hundreds of times successfully. For example, one team wrote it in 1,000 lines of pure x86 assembly. Of course, their team name can't spell awesome without ASM. Okay, so once you get it running, you can launch the codex, and this is what you see. It'll say self-check succeeded, or it'll say self-check failed if your UM doesn't work, or it'll crash. And then it asks you for a decryption key, and this is what you get from registering. And this is specific to each team, and it encodes, actually, as the codex is unlocking itself, it will specialize the codex to that team, okay? So it says it decrypts, it loads, it self-decompresses, it gives you this menu, and of course, having done all this work, you want to choose P and not X, and then P, and it'll print out 16 megabytes, which you'll want to save to another file. And what do you do when you get mysterious binaries from the contest organizers? You launch them in their universal. And the first team to do this was Jabber.ru, 1 hour and 46 minutes into the contest. So they implemented the entire spec and got that running in 1 hour and 46 minutes, which is pretty impressive. And what do you see when you launch it? These are meant to slow me down. Excuse me, to slow me down. Okay, this is what you see. Actually, I've got this running. We can just do it. So I'm going to click the UN button. It's actually much faster than it looks here. This is just because of the way it's interacting with the screen here. So I logged in as guest. And what we have here is basically a implementation, a facsimile of the Unix. We call it Umix. And you log in, and you can see that all of the normal things you're used to seeing, like ls, are there. There's actually some programs left around here by sloppy guest users so we can run a.out, which naturally, segmentation. It'll keep, so you can see there's a bunch of commands implemented. It'll keep telling me I have mail, so let me read my mail. And this is basically what tells you how to proceed. So it's an email from root, and it says, look, guest access is provided as a courtesy. We've noticed that some kind of guest user keeps trying to hack into accounts. And here's an example of something that the guest user did that constitutes hacking. And actually, this is a little tutorial. It tells you what to type in order to start hacking other people's accounts. What you'll find out, though, is the hacking script that was uploaded by the previous guest user actually doesn't compile. And so you're going to need to figure out how to fix that. And so that brings us to the next problem. And the first team that got to this was Team Lazy Bottoms. 2 hours and 11 minutes, right on the heels of Jabber.ru, was the first to get started on this problem. And so this problem is Vic Basic. Okay, so this is just a tutorial. This is just a tutorial, okay, and it's meant to answer the following questions for people that are participating in this contest. Because one thing to understand is the entire contest spec is really just implement the VM and then launch this program. Everything else has to be within Umix and tell you what to do. So it tells you how you make progress, what it's going to be like, and how specifically do you do it. And so basically, the way you're going to make progress in this game is you want to discover account passwords. That's how you're going to get publications, okay, by doing archaeolinguistics. The way you're going to do that is you're going to interact with Umix applications that are sitting in each of the accounts. For example, implementations of programming. And specifically, it shows you how to use the Umix tool. So we have a program called umodem that you can use to upload files. You can download files with this program called cat, and you can look at the files in the directory, etc. Okay, so it's just a tutorial. What's quick basic? It's basic of the ancients. Okay, so it uses actually Roman numerals for all of its numbers. So really, the tutorial is to fix the incomplete password cracker that's uploaded already. The trivial way to do this is you just download it, cut off the end, and then upload it again, because the end is corrupted. The advanced solution is you write some extra loops to just append digits onto the passwords, because that's more secure for some users use secure passwords. Okay, so here's you might want to write your basic program like this. Of course, you need to then change the line numbers into Roman numerals, which is trivial. And then you find that there's a problem that you may not have anticipated. This is the theme of the contest. The Romans have no way to write 0, and you guys are probably used to programming with 0. So, I mean, of course, it's pretty easy to get around this, but it's those kinds of surprises that we like. Actually, in fact, because 0 can't be represented, we don't even allow you to compute 0 by subtraction. Okay. All right, so that's the first problem, and I'm just going to keep going on through these problems as teams solve them, and the scoreboard's going to unfold in front. Okay, that's the basic structure of the talk. So the next problem that we're going to look at was first solved by Team Lazy Bottoms again. They really like to solve the problems first, as we'll see. And they did this in 2.5 hours. So, and this is adventure. Okay. Ominous background. Inference rules. Okay, so let's connect to the UM and look at what that looks like. So Howie, of the Howard Curry correspondence, Password, of course, is xyzzy. And if you look in this directory, there's just two files here. README tells you something about the context, and then adventure is what launches adventure. This takes a little while, but for good reason, which we'll understand in a bit. Okay, room and a door. Room with a door. You're in a room with a mechanical door. You'll probably blah, 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 blah. There's some stuff here. Okay, so let me take the pamphlet. And let me take the manifesto. Okay, let me read the manifesto. Oh, the manifesto is redacted. Okay, let me drop the manifesto. I don't want that. You can't drop the manifesto because you can't bring yourself to part with it. Okay, you can figure this out through the help. I happen to know the commands. Let me incinerate the manifesto. Okay, so I have the ability to not drop things, but burn them forever. And as I do these things, as I learn about the adventure, I'll get these publications. This is a very small one. So let me go north. And here we see a pile of junk. This is the tutorial for adventure. Wow, there's a lot of stuff here. So one of the things we'll find out is I want to get, let's say I want to take the antenna. Okay, you can't take the antenna because there's another item on top of it. Take the other item first. So we have some restrictions on what we can do in this adventure game. Here's another thing. If I look at the A19, let's look at the radio first. Okay, so the radio is broken. It's a radio missing a transistor and an antenna. So like any adventure game, you're going to get some items, you're going to combine them with other items in order to get items that you can use to make progress. This adventure game is a little bit more general. So let's look at the A-1920-IXB. Okay, it's an exemplary instance of part number A-1920-IXB. It's broken. It is missing. It is an IXB missing a transistor, missing a radio that is missing an antenna, and it's missing a processor. So we have items that are broken in higher order ways. Let me go back south now. Here's a special room for the presentation. Salon E. You're in Salon E of the Oregon Ballroom. The door leads east. There's a bullet point here. Let me get that. And there's a slide.ppt you can see here. So basically, you can put these things together. The slides.ppt is missing a bullet point. So slides.ppt. Okay, so the basic goal of the game is you're going to want to build these two items, an uploader and a downloader. Okay, you don't know why yet, but we'll figure that out. Kind of an abstract adventure game. We use the items as propositions notion here. Basically, the way you want to solve this is you want to solve by theorem proving. Okay, so I'm going to show you the actual logic in the next coming slides. The other thing is, because we don't want you to have to write parsers, and because we control all the software here, which is nice, you can actually switch your goggles. So let me switch my goggles. According to the markings, they support English, XML, SXML, and ANSI. Let me switch to XML so you can see what that looks like. So now if I look, you'll get a nice, more easily parsable. And if I prefer a language without so many X's, I can switch to ML. SWML, excuse me. And then I can look, and that actually runs off the side of the screen. But we try to make it easy for you to parse this. You don't have to do the tedious things, although many people didn't figure out there were goggles and then spent a long time parsing English. Sorry about that. Okay, so let's talk about adventure. So like we said, this is we thought, thinly veiled theorem proving problem. There are two kinds of propositions. There's pristine items, items that are not broken. They're broken items. And they're broken. This is a linear language because a linear language because when you use something to fix something else, you lose it. Okay. This is a set of ways it's broken, and it can be higher order. Okay, as we've seen. So, for instance, we can have a radio that's missing the single set of an antenna. We could fix it with an antenna, or we could have a radio that's broken with it's missing a dial, and it's missing a radio that's missing an antenna. Here are basically you can think of the game as a sequence. You want to prove sequence, okay? So there's some pile. I can only pull things off the top of the pile. There's some inventory, which is what I hold currently, and I can only hold a certain number of items. And then I'm trying to make something like the downloader. And there's some rules, like so here we can fix an item partially. So if I have an A and I have something that's missing an A, I can get rid of that, and I gain a slot in my inventory. I could fix an item completely. I can take an item off the pile. I can, once I've actually achieved the item, I can have my initial sequence and finish. So it's I mean, there really is a logic to this book. Now, okay, so you could prove these theorems by hand, but why would you do that? We wrote a theorem prover. We actually started by developing focusing logic. So we're really using PL ideas here to solve this. We have equivalent logic that uses focusing, so it's much more directed search. And then we actually built a pretty sophisticated theorem prover that uses tabling and specializes rules and things like that. Many people actually solve it by hand, and they're actually somewhat large. I didn't get a chance to show you how large they can be. All right, so that's the adventure part one, and we'll come back to adventure in a bit. So here is the next problem. Team Lazy Bottoms again at the forefront of exploring the codex. After 3 hours, discovers this language called 2D. 2D is a programming language with a preposterous two-dimensional syntax. It really is like drawing circuits in ASCII notation, hopefully using fixed-width fonts. And it has a discordantly high-level semantics. So actually, even though it purports to be like circuits, it's really a minimal functional language, okay? So here is the actual code for addition. Just think about parsing this. Our undergrad wrote a parser for this language. You have these dotted lines around the outside, and these are these constructs we call modules. So you can break your program into parts called modules, and they have names. And then you have wires that connect up these boxes. Okay, so the inputs of a box are on the top and on the left. The outputs are on the bottom and the right. And so to give you an idea of how this goes, I'm just going to run 0 plus 1. So 0 is represented as in-R, the injection into a sum type. 1 is in-L of in-R of unit. And so what happens is wires, as this executes, the wires get a value and they keep it forever. This is a functional circuit. And then once a box has all of its inputs satisfied, we can run that box. And we can do this in any order because it's an eager language. So the only one that, so there are two that have all their inputs satisfied, this and this. Let's do the send first. So despite being a two-dimensional language, this is actually linear in the sense that you have to explicitly duplicate and explicitly consume values. So here we're duplicating the 0 that comes in, and we send it along those wires. Then we can do this case analysis, so we check to see whether this thing is an in-L or an in-R. It's an in-L. So to the bottom we send the contents of it. And then down here we see that this one is ready. It's the only one we can run. And in fact, it's a recursive reference to this circuit. So we have recursion in this language. And in fact, recursion is just a particular use of modules. And so, of course, 0 plus 0 returns 0. And then we wrap the successor around it to return 1, and that's the correct answer. So that's basically how this language works. So there are a number of challenge problems. The first was to write multiplication, basically patterning it after addition. It's almost exactly the same. The second was, I'm just going to read it to you. Subject, newsgroups, complaying functional. Subject, reversing a list. Please help. Please help, I need to write a program that reverses a list. Can someone please send me the code that reverses the list? I need the program to do this. Problem 1, 45 points. Create a module called rem that reverses a list, blah, 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 this is spec. Please help, I do not know how to do this and I need to do it by tomorrow. Help, thank you, Sam. P.S. What is a bonus? Now that's basically a tutorial problem. It's easy to solve that one by hand. We wanted to do one that would test your metaprogramming skills. So the more substantial problem in this, of course, what would be a more appropriate way to test a two-dimensional programming language than to build a one-dimensional ray tracer? The ray tracer is a throwback to the 1999 contest, okay, where they made a more conventional three-dimensional ray tracer. What is one-dimensional ray tracing? Well, basically, you have an eye. Eye looks along a ray, and it might see a series of surfaces. Surfaces have reflectance, emission, transmissivity. And we declaratively specify what the color of a scene should be. Okay, we don't tell you how to do it. We just tell you what the correct answer is. So here's some sample images produced by our ray tracer. That's pretty nice. There are only 3 colors that the ray tracer can return. After all, you're using this extremely minimal functional language. So okay, anyway, that's a little funny. the task is you have to design an algorithm that solves this declarative specification. Then you have to implement it in the 2D semantics, which is not trivial. You have to lay it out in the 2D syntax, which is decidedly not trivial. And you have to minimize it for area, because you get more points for smaller programs. Okay? So that is basically the task there. And people had all sorts of ways of trying to solve this. So one team, go to 10, used PowerPoint to do their layout, and then, I guess, transcribe this by hand. Another team wrote a compiler, which is actually a good way. This is kind of what we had intended that you'd do. So you see a very regular layout here where you have these rows where the wires go. In fact, this is much longer than I can fit on this slide. They just lay it out as this extremely long program. That was Team Camel Nuggets. Another team opened up their ASCII files in a proper two-dimensional editor like the GIMP of photo editing software, and then just moved things around. Another team, well, they had a surprisingly small solution. Actually, several teams did this. This one only returns a scene that's all white. Okay, so you may be wondering, that's not correct, is it? Not quite correct. So here's one of our lessons in organizing the contest. We learned that if we were to randomly generate test cases, we ought to do that in a way where the outputs are uniformly random. So we thought if you do 20 tests, then your chance will be something like 1 in 3 to the 20, which is 1 in billions of succeeding at random. But our test cases weren't very good, and that was a mistake on our part. So this is something that we learned. Test a lot or test well. So we didn't do any specific coverage testing, and teams, because they control the codecs, can just run their ray tracer as many times as they want until it works, and then they get a publication they can send to us. Now, on the other hand, most teams that did this also had correct implementations first, so it's not like they cheated. They were just pushing the envelope of the contest, okay? So, but this is something that we saw in a number of the problems, and maybe you could think of it as a limitation of our format. All right, so back to the scoreboard. Well, naturally, Team Apple IIGS was the first to jump right into the quick basic and write the full advanced hacker script. We're not going to talk about that. They also explored another programming language, 6.5 hours into the context, called Wallace. Okay. All right, so balance, well, there's this concept of orthogonality in programming languages, which I'm sure you're familiar with. And I guess the analogy goes something like this. You have your language constructs, which form an orthogonal basis, which you use to get a place in program space. So here's the point I want to get to, and maybe there's like a plus-like thing, and a pair-like thing, and some other kind of like thing. And I just compose those together to get to the program point I want. Balance is all about providing you with a very non-orthogonal language. Of course, those aren't actual vectors, but the instructions aren't that crazy. So what does it look like? Well, it's this 256 byte memory. There are 4 instructions, 4 source registers, and 2 destination registers. And according to the user's manual, because every problem in computer science can be solved by an additional layer of indirection, Balance provides this facility automatically, which is not helpful. Most instructions treat the values of registers as offsets into memory instead of working on the values of registers themselves. For instance, math, in addition to doing this thing where it will subscript, it won't add the registers together, it'll add the memory cells they point to. It also does subtraction first, and then does addition on a different set of registers derived from the first. That's annoying. We have another instruction called logic that performs logical and its perfect dual XOR. We have an instruction called science that tests hypotheses and then can change the instruction speed. The instruction speed is the speed at which the instruction pointer changes, which can be positive or negative and can wrap around. But speed 0 means halt, naturally. And then we have an instruction called physics. Physics manipulates register values directly. It's the only way you can change the values of registers in a linear and angular way. Basically, it works like this. You give it a number, it adds that number to the first register, and then uses that number as a bit mask, bored with the bit mask of the first register, to rotate the registers around. And Team Expansion says, using the physics function instruction feels closer to cryptanalyzing a hash function than a program. This is indeed true, and the programs we used to solve these problems looked a lot like such things. So, okay, in order order to join the balanced certified professional program, you must solve the challenge problems that are inside the codex. And these are actually really quite simple things for most programming languages. The first three are halt the machine without crashing. After that, I think the hardest one is multiply two numbers. Well, anyway, they're not, this is not a very capable language, I guess is my point. So there are a couple of ways you might solve this. One thing you might think about doing it, this is the principled way to go about it, is to use the bad instructions to build up good instructions, and then write your program using good instructions that are the composition of those. Then you might optimize your program. That's how kind of we solve them. You could also try solving these by hand, or generate programs that happen to work, and maybe they happen to work most of the time, and you keep running them until they actually work for you. This can actually be a very difficult process. So here's a cute solution. One of the problems was copy the contents of a register into any memory cell of your choice. So one cute solution is you just fill memory with all the possible values, and then whatever value the register had, it's going to be in some memory location. Several teams came up with that one. Here's a nice, very incredibly nice solution to multiplying two memory cells. This is from Team Smartass. So they go through a bunch of trouble to put the value 1 somewhere in memory. And they have this 3 instructions, incredibly simple loop that uses the fact that balance both adds and subtracts simultaneously in order to write the loop for multiplication. This is a quite brilliant solution. It unfortunately only works if one of the numbers is odd, but it's running until that happens to be the case. And this is, well, it does work. Okay, so that's balance. So there's some more problems, so let's just keep going. About 7 hours into the contest, which problem shoots ahead with the first progress on occult. What's occult? Occult is a Unity-type term language, so it just has constants and application. And so here are some examples. You have 0, you have successor of 0. Add, which is a constant, apply to 1 and 1. But this language, like for instance, this won't step to 2 or anything like that, because there's no operational semantics. What you do is you advise terms by rewrite rules. Okay? So let's write addition. Like any good occult programmer, we start with the blank screen and debug. Oh, looks like you're debugging your program. Would you like some advice? Thanks, I've got advice of my own. Okay, so here's what the program we kind of want to write looks like. And you can already expect that we won't be able to use the program we want to write. Add of z in anything is that thing. And add of the successor of something is the successor of it adding the things. It's just the normal recursive algorithm. And indeed, this will correctly now compute, advise that term, if you will, to 2. What it won't work on is if we have nested adds, okay, which is surprising. And why is that? Well, occult uses a twisted operational semantics. It's aphorism-oriented programming. We derive the operational semantics from quotes by unknown. He's extremely prolific. Advice, when most needed, is least heeded. Okay. So the rule basically is that a rule of advice applies in the subtree of the term with the fewest, non-zero, number of matches. If there's a tie, like in the example we looked at, the rule just doesn't apply. So this makes it really difficult to program. The reason being that local changes to your code have global effects on its behavior, which I don't need to tell you is a really bad way. It makes it very difficult to program. So, okay, so what are the tasks? What you want to do is write addition and multiplication. So you want to basically complete that example. And then there's an XML document optimizer, which riffs on the 2001 contest, optimizing the HTML. Okay? And basically the solutions amount to, well, you want to defeat the operational semantics. This is really easy to do, except that you can't get the program that you want. So what you want to do is you want to make sure that the operational semantics, that annoying rule, doesn't get in your way. One way you can do this is make sure that there's always exactly one rule with one match in your program, and then that's the one place that it can apply. Okay. So one way you can do that is build a stack machine or something where, well, where it's a deterministic application of the rules, saying exactly what it is. You have a cursor or something. Some teams then took their correct solutions and pulled out rules, and then their programs became broken, but they ran them until it worked, until it happened to be accepted. And they got some extra points that way. Okay, so back to the scoreboard. Watrala is on a roll here. 7 hours and 30 minutes in, he's the first one to look at or make any progress on the black knots problem. So let's talk about black knots. Okay, black knots problem, one of the things about this contest is we wanted to have lots of different kinds of problems and of different complexity, so that people who didn't have a lot of time to participate could at least get to a point where they could think about something. And so this is a simple problem, very simple to state. It's not necessarily easy by any stretch. And basically the name of the game is you want to reverse engineer a function. So the story is that there's this child's toy with holes for marbles. There's holes in the top and holes in the bottom. You drop marbles in, and they come out in some place in the bottom, another hole in the bottom, and it makes some number of plink noises. And here's a quote from the specification for the task. I expect children will be very picky about their knockoff toys being observationally equivalent to the 11 official black knot models. You're trying to reverse engineer these toys, and they have to be exactly the same. So here's actually here's an example of black knot. So I drop some marbles into this thing, and you'll see that it's made of these vertical pipes and these crossover pipes. Okay, so whenever the ball goes down a vertical pipe, it just goes straight. When it goes through a crossover pipe, if it goes to the right, then it makes a plink noise. You see that? If it goes to the left, then it doesn't make a plink noise. Okay, so that's black knots. And you need to take the spec, which is just the permutation and the number of plinks that are produced. And there are 11 models that start off small. You can do that one by hand, and you definitely couldn't do the 500 width one by hand. And then you just have to produce a reverse engineered function. The complexity of this problem is unknown as far as we know. If you know, please tell us. The problems in the codex, in general, the problems in the codex were pretty under-constrained. The reason they were under-constrained, well, when we talk about the solutions, we'll see. So they were actually, you could solve them with anything, well, as long as you weren't writing an exponential algorithm, it could tackle many of the problems we gave. Okay, so, whoa, when we're watching the scoreboard, all of a sudden someone jumps way up. And in fact, that's Watrala. 3 hours after he started this problem, he got every single black knot model, which actually surprised us a lot. So how did most people solve this problem? Usually they use this two-phase approach, and it's just a greedy algorithm. They would start by permuting all of the pipes, only doing that, and ignoring the plinks. And then after they had the permutation correct, they would add plinks by doing adjacent swaps, which preserve the permutation. And the reason this works on our problems is that there are usually way more plinks than you needed in order to produce the permutation. If there were fewer plinks, this would be a much harder solution to apply. But many teams did this way. It's a functional programming thing, and you can write it, and you get a lot of points for it. So congratulations to Watrala for that. But I'm getting ahead of myself because before, in the middle of, while he was working on that, we had another Team Lazy Bottoms again, get to a new problem. And this is Cellular automata. That one is not my pun. So what is it? Well, basically we're programming cellular automata, and it riffs on the 2004 contest, aka ants on a grid. So it looks something like this. You've got ants on a grid, and they can only see sort of or smell what's sort of in front of them. And when they move, they have some program that tells them how they turn. So in this case, he turns to the left. He can encounter obstacles like a block, a wall, or a hole, which since he can't smell it, he just jumps right into that, which is bad for him. Or he can find food, and if he finds food, then that's glorious Epicurean success, and that's basically how you win, is finding food. Also, there are other ants, and other ants may be of different clans, okay? There's 10 different clans. Each clan has its own turning machine, which specifies the behavior of that ants in that clan in various situations. It's only 14 bits, so very short programs. Basically, the puzzles are as follows. We give a pattern, which is some constraint. So this is a pattern. Exit means food here, and this pink region is where you're allowed to place ants. And you can use 2 programs. That's not shown here. You can use 2 programs, 2 clans. And what you need to do is find initial conditions, an arrangement of ants and programs, such that some ant gets to some food. So here's the solution to that one. This is our solution. So this ant is here. It's blocking, actually killing these other ants. And then this one will finally reach in and turn upward. Here's a bit more difficult one. You're trying to get, starting from up here, you're only allowed to start up here, you get all diagonally down here. You can get about twice or 2.5 times as far as your starting condition with that arrangement. Some teams found better solutions than this one, actually. When we solved these problems, we both hand-wrote Turing machines and searched by program. But actually, almost everybody solved them entirely by hand or didn't solve them. But this was hopefully a fun diversion for some people. And even if they didn't write programs to write their programs, their Turing machines, then at least they wrote Turing machines. Okay, back to the score. Well, we actually go through, well, there's only one more problem, so that makes sense that we go pretty far. So here's day one. You can see a lot of teams are now and writing their universal machines, which gets them that initial 200 points. And there's a lot of activity up here, fierce race. And about midway through day 2, Kuma is the first freed mind. So this brings us to adventure part 2. Okay, so let's remind ourselves where we were. The story so far is that we were proving theorems. We wanted to assemble 2 items, an uploader and a downloader. So the natural question is, once I've done that, what is the download? What it downloads is your brain. So here's a quote from one of the teams. Are you telling me that I can retrieve the incinerated manifesto? No, Neo. I'm telling you that when you're ready, you won't have to. What does that mean? Okay, so you download your brain, and you see actually that you're a robot. And you're looking at your source code for your brain. You see this data type declaration. So this is in an ML-like language. Type command, these are the commands that you can issue by typing them at the command line. You can try to combine stuff, break stuff, drop stuff. And you also see that there are some data types for the output. This is basically XML. So when you do a command, you can output some XML, and that's what you see with the goggles. And you can also call some functions that allow you to do things like move from room to room, or move items from room to room. And basically, your mind is this function called process. It takes in a command and returns one of these XML data. And it's a big case analysis over the command. And you'll look and you'll see that like the programmer has commented some stuff out. Like if you look at the drop command, which we weren't able to do, it says XXX, do garbage robots ever need to drop anything? And then this code, if you just replace it and then recompile, you can then drop things. Okay? So basically, once you have your source code, you can do anything. You can teleport to any room. You can retrieve incinerated items. They're just moved to the trash heap. You can fix or break items arbitrarily. So all this work you've been doing, theorem proving, is utterly trivial. You can just fix anything with a snap of your fingers. So I guess the question is, what can't you do? Well, let's take a look at how the world is from the perspective of a freed mind. Here's the robot. The robot issues commands via the parser to its consciousness. That's the program. You have control over this. You also have control over what you type. And the robot consciousness can have some effects on the world. It can observe some things. And then its perceptions, which is that XML, goes through this red thing, which is the sensory engine. Okay? The sensory engine will obliterate certain parts of what you see. Okay? And then those go through the goggles, and you see them the way you like to see them for purposes of parsing. Okay, so the sensory engine is why we couldn't read that manifesto in the very first room. It comes out when we try to read it. Its description is redacted. So the goal, circumvent the sensory engine to examine items that have been redacted. All right, so how does this thing work? Well, some item descriptions are classified. It just knows some items that are classified. And so when you try to get the description, it becomes a classified value. And the values that are made from classified values are also classified. So it follows data. If you try to add 1 to a classified value or a subscript of string that's classified, that thing's classified. And control. So if you test the value of a classified value, branch, in both branches, anything you do is classified. Any values you compute are classified. So, and then the sensory engine takes whatever XML document you produce and takes anything that's classified and replaces it with redacted, so you never get to see it. All right, so the sensory engine is a naive information flow system, and this is where we're drawing on functional programming ideas. So what is always the problem with securing information flow? If you study information flow, you should know this, it's effects. So basically, the way you defeat this is by using effects. So here's a hint. One of the room contains a deck of cards. So you pick up the deck of cards. And what you do is you look at a classified item. Once you look at a classified item, anything you compute is classified. But you can have effects on the world. So you close your eyes and you let your subconscious mind shuffle the cards. Then, after the sensory engine has told you can't look at what you just did, you open your eyes again and then look at the cards in the next sort of round of this. And now the room, you've sent yourself a message covertly to tell you what the classified item says. Okay, so that's the basic strategy there. You can do this in actually a number of ways. There's lots of different kinds of effects. You could break items with basically a propositions as data. You can move items between rooms. There's loads of items in the world. Basically everything you've ever incinerated is somewhere. People did both unary and binary encodings, which is of course faster. And once you've done this, once you've defeated the sensory engine, you smash it with a hammer, then harder and larger theorem-proving problems await in the second quest. So if you do this, then your reward is lots more theorem-proving problems to try. Okay, so that is actually all of the problems. So let's watch the scoreboard here for a bit. You see a lot of activity. Basically, there was no slowdown to the number of teams, to the speed at which teams were solving the UM. They just kept on going. And then at the 8 hours before the contest ended, the scoreboard goes dark. And because this talk is a mystery-preserving talk, I'm not going to show you the end of that. We're going to preserve the suspense by talking a little bit about the contest technology. Okay? Okay. Now, we want to make a UM binary. We want to make UMIX and give it out. And we definitely don't want to write this code by hand. So, of course, we wrote a compiler. The compiler compiles a high-level functional language called UML, which is just core SML plus some handy features that are appropriate for the contest. And it's based on my Hemlock compiler that I actually talked about at ML Workshop. But we did a lot of work to extend it. In fact, performance was very important because we couldn't be sure that people's UM implementations would be fast enough to play. We don't want them to have a rough time playing. So Hemlock basically works like this. You have a parser comma error at the top that takes UML and translates it into a typed IL. I guess you elaborate in here too, type check. And you optimize that. Then you do CPS conversion. This is important because the UM has no stack, so everything is heap allocated. That's optimized too. You do closure conversion, and there's a UM backend. And usually the compiler stops at the backend, we keep going. There's a self-printing harness, we saw that. There's a self-decompressor that implements the LZW algorithm. Self-decryptor, which uses the RC4 cipher. The self-check. All of this code actually was in UM. We ended up writing thousands of lines of UM anyway. And then we have this layer that embeds extra stuff in there to confuse you and have little logos and things. The self-check is kind of interesting, so let's talk about that a little bit. We didn't trust the participants' UM, and since basically we really want to trust that our program is verifying it correctly, we want to check that the UM is working properly before we even let them start. So sorry about that, but we don't trust you. The other thing is we want to give helpful feedback, so if you happen to do it wrong, it doesn't just crash, it kind of tells you something helpful. Here's an example. So the thing, if you look at UMIX, the very beginning, or the codex, I'm sorry. If you look at the codex, the very beginning is nonsensical instructions that don't do anything. The reason is they're actually instructions encoded in the wrong endianness, that if you happen to write your UM but you have the wrong endianness, it'll branch off and it'll tell you endian. And hopefully that's enough hint to get you on the right track. It then checks for off-by-1 errors and jumps and things like that, which is another common mistake. And then we try to build up more sophisticated tests once we know that some instructions are working. We actually were surprised the variance in the team's skill levels. So although some teams solved this UM thing really quickly, 2 hours is like par for the best teams, some teams struggled with it for all weekend. And eventually we started to feel really sorry for them, so we made a better self-check. And we spent a lot of time on making a very verbose and thorough self-check. And so we released this standalone benchmark called Sandmark that, then got a lot of people help in implementing their UM and also started performance wars on the mailing list. People ended up actually writing just-in-time compilers and things for this university. They did. Okay, there's also a lot of other stuff in the compiler that we did. So of course it has a garbage collector because it's a functional language. That was also written in UM. There's support for DES encrypted strings because there are certain things we want to protect, even if because they control the environment in which the program runs, they can also look at what it does. We went through some trouble to customize the binaries for each team so that when you submitted a publication, it would take you straight to your team page and you couldn't share that with other teams. There's this obfuscation layer where we take the instructions and we fill in their unused bits with random stuff so that you can't sort of reverse engineer the codex before we send out the spec. Okay, we try to make that hard. There's some more details about this in a technical report that we've prepared about the contest. Actually, a lot of the stuff we talked about, we have a box full of that. It gives away the answers, though, so it's being guarded until the contest is, it gives away the winners. So, another thing we did, the website. So the website has this live scoreboard, and it needs to decode and verify publications. It needs to decode and verify publications, and that code is actually really complicated because it does encryption and proprietary encryption and so on. So what we did is we took our compiler plus the C implementation and just concatenated those together basically. I'm sorry, the output of the compiler and the C implementation. We make a header file that includes a function. So you write UML code and it generates a C function for web server apps. So you can just call the UML basically. And we call this technology UM on Rails. So we're really running the UM, thousands and thousands of publications submitted, tens of thousands actually of publications submitted throughout the contest. We're running through our UM implementation on our web servers. Okay, and then it became like the last 8 hours of the contest, and we thought, well, what programs are left to write? We ended up writing a highly optimized, quote-unquote, reference implementation of the UM. We did that in UM assembly itself. Okay, so this is a 256 instruction interpreter. It's very highly portable. It runs in any compliant universal machine, including itself. The joke here, of course, is that if you can't actually use our reference implementation unless you have an implementation that works. Some people complain about that. So I'm just going to show you. This is the UM running a small hello world program inside our UM implementation, and it just spits it right out. And the winners are. We're getting there. Here's UM and UM and UM and UM and UM. This is 4 levels of self-interpretation on top of that hello world. This is a little slower, and the buffering winners are. We got up to 6 or 7 before we got to get really tired of it. But that's a lot of levels of interpretation, which I think is very, very cool. So, all right. So the winners are. All right. So the judges' prize. Watch this pink line here, emboldened for your viewing pleasure. This is a very discontinuous participant. The reason is that this team consists of only one person, who gets quite high. And actually, that's the final score. We're not showing anyone that's higher, so you're not going to see the top 3 teams beat him. And so, the judges' prize for lone hacking with 4,939 points. The judges declare that Witrala is an extremely cool hacker. All right? So, we were able to ask the current Museum of Natural History for pieces of the codex that we could share, now that we've decoded it. So we've got these personalized. This is volume ID J. Carl, congratulations. Excellent job. Really cool hacking. Okay, so that orange team also about to make some progress there. Jumping up. Okay. Beating out hundreds of teams in 3rd place. Can't spell awesome without ASM. 5,328 points. The judges declare that the language of choice, assembly, is not too shabby. Wow. All right, back to the scoreboard. I know we have to repaint it. What?
Who are the members of the team?
Could you tell us the members of the team?
Myself, John Etheridge. The other 3 team members were Reed Barton, Tomek Chaker, and Ralph.
From where?
First place.
Poland, Harvard, and a Google intern.
And Watrala is Carl Whitty. Okay, so sorry about the suspense. So in second place, Kuma, with only 2 points more than third place, 5,330 points, has declared that D is a fine tool for many applications. You're welcome. Yes, tell everyone who's in the team if you like. I don't have to listen. I can't speak English.
So we are 4-member team from University of Tokyo, and it's all these. I'm Kazuhiro Inaba. I'm the B programmer and standard, and he's Yusuke Endo, and her Nayuko Watanabe, and one more team member is not here. Sorry.
All right, that's second place. And the Green Machine, who led for the last day and a half of the contest at least, and who won by more than 2 points, although I hear that they spent 2 weeks of CPU time getting their last 2 points, is Team Smartass with 5,428 points, more than we thought was even possible. The judges are very happy to declare that their programming language of choice, 2D, is indeed the programming language of choice for discriminating hackers. And they're discriminating hackers indeed. Great job, guys. Say your names, perhaps.
Christopher Hendry was sort of the person that wrote this all into it. This is Daniel Wright. He's done the ICFP several times before. This is Derek Kissman, and I'm Ambrose Feinstein.
From Google. Yeah. I know. Yes. Well, so a couple more slides, very short. Our future work. We were going to prepare a permanent offline codex for fun and teaching purposes. We think that the contest stands well on its own, and 230 people have done it without any chance of winning after the contest ended. And this is going to be at boundvariable.org. That's its permanent home. Look for changes in that soon. We're going to fix some of the problems that we discovered in the beta testing. And then I'm concluding with a quote from Jean-Paul Sartre, 77. He says in the codex, "Hell is other programming languages." All right, thanks for listening, everyone. Really good actors. Okay, so we have this technical report if you want to get it. We're going to have, I guess, we have copies here, and we have copies, I guess, at the ACM table. So, again, thanks for listening, and try out the codex. It's really fun, although I spoiled it, so you already know. Are there any questions?
Next year.
What's that?
Next year.
Next year what? No, I need to graduate. Okay. Good luck.
There's a reception upstairs, Mount Hood room. Come have a drink and celebrate.